How long have we been down here?
Oh, I don't know, it feels like ages, but oh, you're in Czech, by the way.
I'm in Czech. Oh. Oh no, I'm safe. Got you this time.
Oh. Anyway, we should probably do the video, right?
Yeah, we should.
Yeah. I think we've eluded the physics police for now.
Yep, hey, cool on. So, there's another equation, a new equation.
Another equation. In the first video we said, we'll use this equation, but it's often used for lots of things. So now I'm going to use it for lots of things.
Yeah, so, to remember the first video, it's E equals F over Q. That's lovely.
That's one of the equations for that, but there's another one which has the same value.
It is. It's E equals, and it's V over D.
It is.
Which is voltage, or potential difference,
over the distance between the two magnetic plates.
Yes, because that's what this is applicable for, is when it's between two plates and stuff. So we've now got two equations for E. This is where we begin to actually use them, because we very rarely need to use the individual equations on their own.
Often we combine them, so that's what we're going to do. We have a very large worked example we're going to go through.
Yep, but it's sort of applying to a real situation, which someone actually did.
Someone actually did do it. This is when they were trying to work out the charge on the electron and found the coolest way to do it ever.
Yep, so he basically did this experiment that we're now doing the maths for. So, oil of density 810 kilogram per metre cubed, that's the density of oil, is sprayed as a fine mist into a space between two horizontal plates. So already we're thinking we're probably going to be using these. I mean, you probably gathered that from the title of the video anyway. But
yeah.
These plates are 5 millimetres apart, or 5 times 10 to the minus 3 metres apart.
That's not drawn to scale.
No, Clever Cracker images are not drawn to scale because that would be ridiculous.
Yeah.
I can't draw a nanometre. One oil droplet of radius 5.6 times 10 to the minus 7 metres.
Okay.
So we're now talking about a single one of these droplets and its radius, so 5.6 and 10 to the minus 7, has a charge on it equal to that of a charge on a single electron. So, I mean, we know what that is. It's the charge on an electron. But anyway.
That's what we're finding out essentially.
This droplet is observed through a microscope to remain stationary between the plates. So this thing with this radius is not moving.
So that's important.
And it's in there, and this has got a potential difference of 183 volts between these two plates. Then it says calculate the charge on an electron. Now, this charge is equal to the charge on an electron, so we can work out the charge of this particle, and it will be the same. And that's actually how this guy did it. Well clever.
Well clever. So, what do we have?
Well, that's always a good question. We go to these equations. What do we have? Good question.
Yeah. We do not have the field strength, so
I'll put it in red.
Yeah.
We do not have this.
We do not have that. We don't have the force. We haven't got the charge, but we want the charge.
I'm gonna do that in like a squiggly thing. We need that, but don't have it.
Yeah, but we have a voltage and a distance.
Absolutely.
Yeah. Now I want to eliminate as many unknowns as possible to start with. I don't think we're going to find out the field strength.
I don't think we are. Looking at what we've got, we can't work out the field strength. Well, we could work out the field strength as V over D, then we'll just be equating them anyway, because we need to use this equation. It's the only one with Q, which is what we need. So we're going to be using V over D, because we've got them. So just get rid of that. I'm going to put a line through it.
So ignore that for now. Q is our final result. It's not going to be an easy one-step thing, so I'm thinking, how do we get F?
Yes, we need F in order to work out Q from what we've got here.
Alright, so what do we have here?
Well, the force is acting on this one droplet, so really it is a fine mist.
Yeah.
We can just ignore the rest and think of the one particular droplet. What are the forces on it? That's the question.
That is the question. It's not moving, so it hasn't got any acceleration to do the plates up or down, but it has got its weight.
It's always got its weight, and that is in fact the only force acting on it. So this force that's in this equation for this droplet will be equal to its weight. Now, we know its weight is equal to mg, mass times gravitational field strength.
We don't have mass.
Not yet. Is there a way to work out mass from what we have?
I think there is one, because we have density, and in its units there is mass, so we might have to find it somehow.
Yep. And the other units is meters cubed to the minus 2, which is like an inverse of volume. So if we times that by volume, and we have a radius here, so we could do that, then we're rearranging the equation density equals mass over volume.
Yeah. Okay, so what mass? So
that's rho times V, or density times volume. So firstly, we need to find out the volume. It's the volume of the sphere.
Yeah.
It's a spherical oil drop. So we're using...
As they all are. So using, this is in your formula booklet as well, and that's 4/3 of pi r cubed.
So I'm going to put r in place of it now.
Oh, I see. Okay, that's good.
R is 5.6 times 10 to the minus 7. It told you that in the equation.
Calculating things.
and that is cubed. As Trev said, there's lots of mathematical relationships in your booklet that aren't in like the typical equations part. It's at the beginning, but make sure you make good use of them. If you can't remember, or if you're a little bit edgy on your GCSE knowledge, it could be a difference between a mark.
Yep, so what we have is we have 7.36 times 10 to the minus 19.
And that's our volume.
This is our volume. So now we have the volume, we can times it by the density which we have here.
So mass equals density times volume, so that's 810 times
our
our volume, which is 7.36 times 10 to the minus 19. I'm a little bit slower than Trev.
That's fine. And that gives us 5.96 times 10 to the minus 16.
To the minus 16. So that's
Yes.
our mass.
So we have a mass, now we can times it by the force of gravity to find our weight, which is our force.
So we've got mg, 9.6
Yeah,
times 10 to
we
the
know the
minus
force of gravity is
16.
9.81. That's what we're timesing it by now.
I'll put it in brackets to be neat, so it doesn't matter because it's multiplication, but just to be neat and sure
Yeah.
what we're doing.
Okay, and that gives us 5.885 times 10 to the minus 15.
Times 10 to the minus 15.
Yes.
Lovely.
So
Lovely,
now we
lovely,
have
lovely.
force. Now we can measure under this equation up here.
Yeah, so I'm gonna write it up again, but
Yeah.
down here.
So we've got our force, we have everything apart from our Q now, so what we want to do is rearrange to find the charge.
So what we can say.
Yeah, what we can
Remember
say.
what this implies. That's what this implies if you're not familiar with that.
Yeah. So we have Q is equal to VD over F. Or is it F? Oh, sorry, FD over V. Mix
Because
them
you're
up.
taking F and dividing by this, and when you divide by a fraction, you flip it and times it.
Mhm.
FD over V.
Yeah.
And now we have all of these things.
We do.
So I'm going to write it up while Triv types into a calculator. We get Q equals F, which is our force, which happens to be our weight.
It is.
5.85 times 10 to the minus 15
Yeah. Times our distance between the two plates, which is 5 times 10 to the minus 3.
is indeed.
And then we divide it by our voltage, not another volume, and that's 183.
Is indeed. So it's
And
a
that will
potential
give
difference,
us-
and that will give us a charge.
Of 1.59 times 10 to the minus 19, which we can round up to 1.6. And we know that's a charge of our electron, so we know they got the answer right, and everyone's really happy.
Yes, it's good when it's a show that question like this, and we can get to the right answer.
Yeah.
Probably wasn't as good for the scientist who first worked it out and went, "Well, is this right, or have I made a silly error?"
I mean, it's pretty complicated. Yeah, but that's how he did it. That's how we did it, and that's the kind of thing they do with these equations. It's not.
It is.
These equations are quite easy to mess around with.
They
Unlike
are
the one in the
indeed.
previous video, which is quite big, so they make the content hard.
They do indeed, and it's the approach that's hard as well. Is this you don't know F? How can we find out F from
Yeah,
what we've
so
got?
I'll think
Can we-
about writing down lots of equations about how to find the different unknowns is a good step, and eliminating unknowns is always important.
Yeah. So think about everything you've got. Try and think of the bigger picture, even if you don't need to.
I mean, since Suvat, I've always wrote everything I have, everything I need along
Yeah.
the side.
Since AS, yeah.
Yeah.
Absolutely.
So I think that's a good way to do it.
Clever cracker tip. So now we can get a cup of tea. Now that
Yeah.
the physics police have gone.
Oh, I think we're going down.
Well, you are, because I'll put you in check.
Ah!